to finish off our discussion of TFL proofs, we need to talk about a few derived inference rules. We have discussed 12 basic inference rules, and in each case, we justified these basic inference rules by extra logical considerations, meaning by claims about what kind of inferences we encounter in everyday life and find plausible. So for example, when we introduced conjunction introduction, we just said, well, naturally, if you have shown that A and you also have shown that B, you can infer that A and B. That's just a very natural and plausible inference. Now, derived inference rules are different. We do not justify them by extra logical considerations. Rather, we can prove that they are valid using our basic inference rules. So we derive the derived inference rules from our basic inference rules. What that means is that whenever you use a derived inference rule, you are effectively saying, I could prove that this step is valid using only basic inference rules, but I'm skipping these steps. Instead, I'm just citing the derived inference rules and ask my reader to trust me that I could spell out the proof if needed. Overall, we have 9 derived inference rules for TFL. We've already encountered the rule reiteration, which is in fact a derived inference rule. And then we are now going to meet a few additional ones. So disjunctive syllogism, modus tollens, double negation elimination, excluded middle, and 4 different De Morgan rules are all derived inference rules. So why is reiteration a derived inference rule? On the left here, you see the rule. If in one line of your proof you have established that A, reiteration licenses you to simply repeat A. Now that's the rule, but we can in fact prove this rule using only our basic inference rules. So suppose that in line 1 of my proof, I have A. Could be a premise, maybe I have already established this line. I can then use conjunction introduction applied twice to line 1 to infer A and A, and then I can infer A by citing conjunction elimination as applied to line 2. So what I've shown here is that whenever I have A in my proof, I can infer A. And that's just what the rule reiteration tells us. Now, you may notice that here on the right-hand side, I used meta variables in this kind of curly font to give my proof. This is important. So what I've given you here is not simply a proof, but a proof schema. Basically, I have argued that whenever you have a sentence of the form A, you can infer a sentence of the form A and then infer a sentence of the form A and A again. So, for example, if you have a conditional if A then B in your proof, you can infer the conjunction if A then B and if A then B, and then infer if A then B again. So this would be another instance of my proof schema. Our second derived inference rule is disjunctive syllogism. Disjunctive syllogism tells you that if in one line of your proof you have a disjunction of the form A or B, and in another line of your proof you have the negation of one of your 2 disjuncts, then you can infer the other disjunct and cite disjunctive syllogism as applied to lines M and N in this case. Now, this rule intuitively is extremely plausible. If either A or B is true and A is false, well, then B must be true. So we could justify this rule by these kind of considerations that I just put forward. but we can also prove the rule using our basic inference rules. So here on the right-hand side, you again see a proof schema. Suppose in line M we have a sentence of the form A or B, and in line 2 we have a sentence of the form not A. We can then start a subproof that starts with the supposition that A, infer bottom, citing bottom introduction, infer B, citing bottom elimination. And we can set up a second subproof that starts with the assumption that B and simply reiterate B. And then we can infer B by citing disjunction elimination as applied to line 1 that contains our disjunction, and the two subproofs from 3 to 5 and from 6 to 7. So that's the proof schema that establishes that disjunctive syllogism is a valid rule of inference. I am not going to prove the remaining derived inference rules for you. We are going to leave that as an exercise to be done in class and in the problem sets. I'm simply going to tell you what these inference rules allow you to do. So here's the next one, modus tollens. Modus tollens tells you that if in one line of your proof you have a conditional of the form if A then B, and in a different line of your proof you have the negation of the consequent. In that case, you can infer the negation of the antecedent and cite modus tollens as applied to lines M and N to justify this inference. And again, this rule is very plausible. A conditional is true in all cases except when the consequent is false and the antecedent is true. So if line M tells us that the conditional is true, and line N tells us that the consequent of the conditional is false, that means that the antecedent of the conditional must be false, since otherwise it would be impossible for the conditional to be true. Our next derived inference rule is double negation elimination. Double negation elimination is very simple and very plausible. Suppose that in line M, you have a sentence of the form not A. You can then infer A and justify this inference by citing double negation elimination as applied to line M. And this rule should be obviously valid, given that if it is not the case that not A is true, well then A must be true. Our next derived inference rule is a little more complicated. It is called excluded middle. And excluded middle is based on the thought that either A or not A must be true. And then excluded middle formally goes like this. If you have a subproof that starts with the assumption that A and leads to the conclusion that B, and you also have a subproof that starts with the assumption that not A and likewise leads to the conclusion that B, you can then infer B and justify this inference by citing the law of excluded middle as applied to the two subproofs from M to N and from M prime to N prime. So again, the basic thought is, well, either A is true or not A is true, and if in either case B follows, well then B must be true. Finally, we have 4 derived inference rules that connect negated disjunctions and conjunctions. These 4 rules are called the De Morgan rules, and I'm going to start at the top left corner. The first De Morgan rule tells you that if in line M of your proof you have a sentence which is a disjunction where both disjuncts are negated, so a sentence of the form not A or not B, you can then infer that it is not the case that A and B and cite De Morgan as applied to line M. Now if you think about it, this rule should be valid. It is extremely plausible. If either A is false or B is false, well then it cannot be the case that both A and B are true. Let's look at the second De Morgan rule in the bottom left corner. The second De Morgan rule tells us that if in line M of your proof you have a negation of a conjunction, so you have a sentence of the form, it's not the case that A and B. You can then infer a disjunction where both disjuncts are negated, meaning a sentence of the form not A or not B. And again, this is extremely plausible. If it's not the case that both A and B are true, well then either A must be false or B must be false. And that's just what the De Morgan rule tells you. Let's next look at the top right corner. The third De Morgan rule tells you that if in line M of your proof you have a conjunction where both conjuncts are negated, so a sentence of the form not A and not B, you can then infer a negated disjunction, meaning a sentence of the form not A or B. And again, this is very plausible. If both A and B are false, then the disjunction A or B can't be true, given that the disjunction A or B is true if and only if either A is true or B is true. And then our fourth and final inference rule is in the bottom right corner. This rule tells us that if in line M of your proof you have the negation of a disjunction, so a sentence of the form it's not the case that A or B, then you can infer not A and not B. Why is that? Well, if it's not the case that A or B, that means that both A and B must be false, since otherwise the disjunction A or B would be true. Here's a proof illustrating the use of derived inference rules. In this case, we have three premises. The first premise is a conjunction, M or N and O or P. The second premise is a conditional, if N then P. And the third premise is a negated sentence, namely not P. And what we want to establish is a conjunction M and O. Now, backward planning suggests to me, look at what you want to prove, a conjunction, and use the corresponding inference rule. So backward planning suggests to me I should prove both M and O separately, since then I'm able to infer M and O by citing conjunction introduction applied to these two lines. So how can I prove both O and M? Well, now I'm gonna look at what I have and apply some forward planning. So my first premise is a conjunction, and I'm just gonna go ahead and apply conjunction elimination to infer both conjuncts M or N and O or P. I can justify this by citing conjunction elimination as applied to line 1. Okay, let's do a little more forward planning. In line 2 and 3, I first have a conditional, if N then P, and I have the negation of the consequent of that conditional. So I can apply the rule modus tollens in order to infer the negation of the antecedent, in this case not N. So I'm going to cite modus tollens MT as applied to lines 2 and 3. And now I see that in line 4, I have the disjunction M or N, and in line 6, I have the negation of the second disjunct. So now I can infer M and cite disjunctive syllogism as applied to lines 4 and 6. Okay, what's next? I have established M. That is in fact one of the lines that I wanted to prove down here. So, So I could either erase what I just wrote here and just supply the justification disjunctive syllogism down here. What I'm going to do alternatively is I'm simply going to use the rule reiteration applied to line 7. Okay, we still need to prove O. How can we prove O? While in line 5, we have the disjunction O or P, and in line 3, we have the negation of the second disjunct, not P. So that means that we can again use disjunctive syllogism in order to infer the other disjunct, in this case O. So I'm going to do that down here. We want to prove O, and I'll just supply my justification, disjunctive syllogism, as applied to lines 5 and 3. And now I just need to fill in the gaps. So number my lines 9 and 10 and supply the justification for the final step, which is conjunction introduction as applied to lines 8 and 9. So that's our completed proof. We used 2 derived inference rules, modus tollens and disjunctive syllogism, and we also used both backward planning and forward planning at several points in this proof. Let's sum up our discussion of TFL proofs. In the past 2 lectures, we have encountered 12 basic inference rules. 2 rules for each one of our main connectives, plus 2 rules for bottom and indirect proof. So this may look like 13 basic inference rules, but we have seen that bottom elimination and negation introduction are in fact the same rule. So there are 12 basic inference rules. And then we have also seen that we can derive 9 inference rules from these basic inference rules. So that means that in addition to our 12 basic inference rules, we also have 9 derived inference rules. And then we studied 3 main proof strategies that allow us to construct proofs using these rules. In the next lecture, we are going to move on and do some meta theory, meaning we are going to discuss the relationship between truth tables and TFL proofs.